So we'll start at 1:10 for the Columbia folks, but if people have questions, they can ask questions now while we wait a couple minutes. Pardon? I just sent an email out that we have a special seminar at Columbia at 3. So I can't do a problem set tomorrow, but for people who can stay longer, we'll have a problem session tomorrow for like 45 minutes after class. And then race up to Columbia's other seminar tomorrow. And then I can't remember if I've posted an answer key yet for problem set 1. There is an answer key. So I can post it tonight. There's always an answer key.
Well, some classes they don't put them. That's not.
And the question of is there an answer key? I'm always happy to have a question that I can answer. So this is where we left off last time, where we had worked out now with our density matrix, what the one pulse experiment looked like. And either comforting or disappointing, after a lot of complicated mathematics, we got the same answer that we had from the block equations. And as I said, if we just had an isolated spin, we wouldn't bother with any of the density operator stuff because the block equations are a perfectly fine description of an isolated spin. But that this formalism is suitable for more complicated spin systems and more complicated Hamiltonians. So we need a way then of treating in this density operator formalism, say a 2-spin system. And of course, once we do that, it's obvious how to do 3 spins, 4 spins, etc. And importantly, something that we'll emphasize more a little bit later, perhaps, is that the Hamiltonians that are important in at least the kind of NMR I'm familiar with are all pairwise Hamiltonians between pairs of spins. So fundamentally, once you analyze a pair of spins, you know pretty much fundamentally how everything works, because if you have 3 spins, you don't have a Hamiltonian with a 3-spin term in it. You just have pairs of 2-spin interactions to handle. So the question is how to generate the density operator representation for 2 spins. And since the operators all have matrix representations, we're going to do it first by developing the matrices. And then, as I've said before, since we don't like looking at matrices, we'll then assign symbols to the matrices. A lot of the rest of this particular lecture shows that if we multiply all the matrices together, we're going to get the answers we expect. For example, you already know that if you have 2 spins with the J coupling, you expect the I spin spectrum to be a doublet. You expect the S spin spectrum to be a doublet. So there's a lot of matrix multiplications in the slide deck to show that that's the case. But I'm mostly today going to skip over most of all the matrix multiplications. You can look at that on your own because we want to get to the point in the notes where we start to replace the matrices with symbols and work out the symbolic manipulation, because that's really what you do most of the time. If you get to a situation where you need to do a lot of actual matrix calculations, you're not going to do that on paper. You're going to use a program like Spinach or Spin Evolution, et cetera, to do the calculations for you, because obviously the computer doesn't care about multiplying matrices. And it turns out it's what we need to do to generalize is very simple. So very simple, if I can get this to work. Remember, for the single spin, a wave function was just a column vector with two entries, a 2x1 column vector, so that alpha was the column vector 1, 0, beta was the column vector 0, 1. And it should be kind of clear if we have two spins, we have the alpha alpha state, the alpha beta state, the beta alpha state, beta beta state, and that's going to need to be a column vector with 4 entries, a 4x1 vector. And we just have to know, how do we construct those 4 vectors? And the formal way is to do something called the direct product. So that if we need an n spin, or the wave function for k spins, if we need the kth wave function for n spins, we take the direct product of the wave functions for each individual spin. So spin 1 might be the alpha, spin 2 might be the beta, spin 3 might be alpha, spin 4 might be alpha. All we have to do is take the direct product of all of those. And the total spin quantum number is just the sum of the individual quantum numbers. And there's a definition of a direct product. So the direct product is shown by this circle with the multiplication sign in it. And it's ordered. So A direct product with B, each element of A is multiplied by the matrix B, so that the full dimensionality of the matrix then increases. And here's just examples for the alpha alpha state. The I spin is the column vector 1, 0. The S spin is the column vector 1, 0. When we take the direct product, we then get 1, 0, 0, 0, representing the alpha alpha state. And for alpha beta, you can see all I do is change the second vector to 0, 1. And now I have 0, 1, 0, 0 by my recipe, because I take the second column vector, multiply it by each element of the first one, and that's the expansion. And similarly, beta alpha and beta beta. And I just have 4 vectors, and there's a single 1 somewhere in the vector. And you might notice that the way the direct product got defined is kind of the second spin state changes first. So in the ordering, the first position in the vector is alpha alpha. The second position is alpha beta, then beta alpha, and then beta beta. So if I had 3 spins, I would use it, changing the spin state of the third state first, then the second spin, and then the third spin. So when I write these out, I kind of go right to left, varying the indices and the rightmost side first. That's sort of arbitrary. We could have done it the other way, but then we wouldn't have adopted this direct product that the mathematicians had already thought up. So rather than inventing our own matrix algebra, we might as well use the matrix algebra that already exists, since it doesn't make any difference. It's just arbitrary labeling. There's supposedly the story that when Heisenberg was working out matrix mechanics version of quantum mechanics, that he had no idea about matrices. He just had column of numbers. And he's supposedly riding in the train, and by accident, the other person riding in the train was the mathematician who said, "What are you doing with matrices?" And Heisenberg apparently says, "What's a matrix?" When it comes to operators, we're going to do exactly the same thing. We had our Cartesian operators that were 2x2 matrices. And now if we want to expand up, we're going to have the direct product of two 2x2 matrices, and we're going to end up with 4x4 matrices. So here's an example and here's the trick, or a trick you have to know. Again, if we have n spins and we want to work out some operator, we just have to take the direct products of all the operators acting on each spin. And something that always gets done, even though it can be, I mean, typographically it's nice, but it's confusing for students, is that we always have to remember that there can be identity operators. So here, for example, if I want to know what the matrix representation is for IZ in the IS spin system, I have to take the direct product of the one spin operator for IZ, which is a 2x2 matrix, and to expand it up, I have to take the direct product with the identity matrix for the S spin. And that's, the math is shown here, that's fine. But normally we don't write this superscript 2 spin and superscript 1 spin. Normally only IZ is written, and you have to know yourself, am I talking about 1 spin, in which case I have a 2x2 representation, or do I have the 2 spin, in which case I have a 4x4 matrix representation. And that'll be true through the whole class or the whole theory. And you'll see, periodically I have to remember to insert the identity operator for spins that don't appear explicitly in the symbol. So now, does this make any sense? Well, this is, imagine over here that I had a column vector, one of my 4x1 column vectors, and I'm going to multiply them. So this clearly picks out the first position in the column vector, but that's the alpha state. This picks out the second position, which is the alpha beta state. And then I have a subtraction of the beta alpha state and subtraction of the beta beta state. So that says for the 2 spin system, the magnetization for the I spin is the sum of all the states where the I spin is alpha minus the sum of all the states where the I spin is beta. And in this case, then, the I spin is alpha for the alpha alpha state and the alpha beta state, and the I spin is beta for the beta alpha state and the beta beta state. And luckily, this matches our expectation. We think I spin Z magnetization of the I spin is the difference between alpha and beta for the I spin, and it doesn't matter that it's distributed amongst different states of the S spin. And similarly here, if we do the same thing for the S spin, now I have the identity operator for the I spin and direct product of the 2x2 matrix for the S spin. And again, the order matters completely here. And now I see I have the alpha alpha state, the beta alpha state, minus the sum of the alpha beta state and the beta beta state. So now I have the difference between the S spin in the alpha state minus the S spin in the beta state, again, making proper sense. These are called product bases for obvious reasons. They should be called direct product bases, but we tend to, everybody knows product means direct product in NMR. There are other bases, but of course we can always do a unitary transformation to switch from one basis set to another. Now, we want to know now how some operator in the two-spin case acts on some wave function for the two-spin case. And in my symbols, I'll start to represent the operators as the product, by which I mean the direct product, of an operator for the I spin and an operator for the B spin. So, but of course, sometimes one of these won't appear because it's the identity and I'm not going to write it. But the direct product of A and B is, of course, this. The cat for being in the ith spin state of the I spin and the jth spin state of the S spin is also a direct product. And the I spin operators only act on the I spin cats, and the S spin operators only act on the S spin cats. So I can distribute this then and say that the answer is whatever the I operator does to the I spin cat, direct product with whatever the S spin operator does to the S spin cat. There's also a terrific simplification. So here, for example, if in the two-spin case I have IZ, that really means IZ direct product with the identity operator for the S spin. And if it's acting on the alpha beta state, that's the direct product of the alpha cat with the beta cat. But the I spin only acts on alpha, and that gives back 1/2 alpha. And the identity operator for the S spin only acts on the ket for the S spin, and the identity operator gives back beta, and their direct product is the alpha beta ket, and I just have picked up this factor of 1/2. And of course, very quickly you stop writing these things out. You just recognize IZ only acts on alpha, that gives back 1/2 alpha. There's no S spin operators, that's the identity, so nothing happens to the beta spin, and you write this down directly. And if I take the matrices and write them out and do the multiplication, I get the same result. And what we're going to want to be doing is manipulating these symbols rather than multiplying these matrices together, because you're happy with symbols and unhappy with matrices. But anytime we're stuck, we can always go back to the matrices and work out what we should do, how the symbols should work, if we don't know the recipe for the symbols. So here's another example. 2IZSZ as some matrix representation, but I know I should apply the IZ operator to the alpha state, and that's going to give 1/2 alpha. And the SZ operator to the beta state will give minus 1/2 beta. And then so 1/2 times minus 1/2 is a minus 1/4. And then this 2 gives minus 1/2 alpha beta. And again, I can figure out what this matrix is by doing the direct product. So here's the matrix. I multiply the matrix by the vector for the cat, and I get the same answer as from the symbolic manipulation. And then why the 2? The 2 is because I want the basis operators to have the same norm. And remember, the norm was that I take the trace of the adjoint of an operator times the other operator. So in this case, the norm for a given operator would be the operator's adjoint times direct product with the operator itself, and then take the trace. And in an ideal world, I would normalize the operator so that trace would be equal to 1. That gives rise to a lot of numerical factors floating around. But it's sufficient to normalize the operators to some arbitrary number as long as I normalize the operators to the same number. And in that case, I can always renormalize when I need to. Most of the time, I don't need to. It's important that all the operators be normed to the same norm, because otherwise, when I do these transformations, I'm going to be stretching or contracting how much magnetization I have. And just like for the unitary transformations, we don't want to do that. We don't want to do that here. And you can see perhaps right away, if I come back to this operator, where did I do it? Here, this operator, if it's real, so its adjoint is the same. So if I multiply the operator by itself, I'm going to get a diagonal identity operator. If I take the trace, I'm going to get 4, and then this would have been squared. So I'm going to get unity here. And you can easily see I'm going to get the same norm here, because when this is multiplied by itself, again, I'm going to get a trace that's equal to 4. This will have been squared. So these are going to be normed to 1. That wouldn't be true if I didn't have this factor of 2 here. So the factor of 2 got introduced to make sure that the IZ operator and this 2IZ SZ operator had the same norm. Yep.
Are the one-spin operators also normalized to?
Well, we can go back and look. So here's the one-spin operator. When I square it, I'm going to get a diagonal element, and the trace is going to be 2, but this 1/2 is going to be squared, and I'm going to get a 4th. So the norm is going to be 1/2 rather than unity. If I wanted to norm this to be unity, there's going to be a factor of √2 here. And I just hate writing the factors of √2. And you'll see in many cases, there'll be times when I have to put in a properly normed identity operator. Here, I just need the identity operator because of, well, it's somewhat a matter of convention. In if I take the identity operator and square it and take the trace, I get 2. And we just decided here, when I take the trace, square and take the trace here, I'm going to get a 1/2. So my identity operator here isn't normed the same as the IZ operator. So in principle, I should have a factor of 1/2 here as well. But all that does in this case is change the overall norm here. and it's conventional to do it this way. And again, as long as everything is normed within a given basis, as long as things are normed the same, it doesn't matter. But you'll see, because of this difference, there'll be times when I have to put the half in for the identity operator, the half times, if this is how I define the Cartesian operators. So sometimes you can be a little sloppy. Okay, so now we can generate these symbols and matrices. The question is, what do the Hamiltonians look like? And Anne will talk, about the dipole Hamiltonian later on. In solution, the main other Hamiltonian that we need to talk about is the scalar coupling Hamiltonian, and it's shown here. This factor of 2 pi is there because when people first measured the J coupling splittings, they were working in Hertz. So J is defined in Hertz. So to get proper frequency units, we have this factor of 2 pi. And then there's this scalar product of the spin of the I spin or the J spin, summed over all possible spins. So for a 2-spin case, we would just have 2 pi J I dot S. Now, this dot product, the scalar product, of course, would expand out, say, to IX SX plus IY SY plus IZ SZ, just like any normal dot product. In solution, or in all NMR, there's something called the weak coupling limit, where the J coupling is much smaller than the frequency difference between spins. So here, for example, let's suppose we're talking about the amide hydrogen and the alpha hydrogen in a protein. That scalar coupling ranges from close to 0 to maybe 12 Hertz. The difference between the amides hydrogens and the alpha hydrogens in a protein is of order 3 or 4 parts per million. So on a 500 megahertz spectrometer, that's over a kilohertz. So 12 Hertz is certainly way less than a kilohertz. So in that case, one is in what's called the weak coupling limit. And in that case, we can ignore the parts of the Hamiltonian that don't commute with the B naught field. And formally, I think this is called truncation. And if it's not called truncation, Anne will interrupt at this point. And that's a great simplification in solution. And in fact, it's one of the great things about working on bigger and bigger magnets, because the J coupling is independent of the magnetic field, but the chemical shift differences between spins get larger and larger and larger as you go to larger magnets. So as magnets have gotten larger and larger, the weak coupling limit becomes a better and better approximation. And at this point in a protein, there are almost no strong couplings left when you're up at 800 megahertz. Maybe some of the proton or carbon couplings in like a phenylalanine ring might still be pretty close. But to a very good approximation, everything is weakly coupled in a protein anyway. And I know 0 about RNA, so you'll have to ask Hashim when it comes about DNA and RNA. So, yep.
Why does J coupling not depend on how spins are oriented?
So it's a tensor. The J coupling is a tensor. Yes. And we're talking here about the isotropic part of the tensor, and the other parts of the tensor have either no or extremely hard to observe effects on the spectra. And when people ask me questions like that, I say, Anne will talk about it later when she talks about tensors and asymmetries.
At least in principle, it is a.
In principle, it can be a 3 by 3 tensor. And so actually there's a mistake, because this is still, looks like the strongly, or I don't need the dot there, I guess, anymore. The dot should not be here. Now, here I have IZ for the one spin, direct product with IZ for the other spin. And remember, the way I defined these a slide ago, this had a 2 in front of it. It was 2IZ SZ for the normalization. So to get the normalization right here, it's conventional to move this 2 over here, in which case the frequency part is only pi times j. That 2 got stuck into a normalization constant. And that is kind of an obscure and tricky part of this, that actually, if you look at the second edition of the NMR book of Anna et al., the back cover that was supposed to summarize all the results forgot to take the 2 out. So the back cover of the book is wrong because of this. Anyhow, then in the rotating frame, this is a time-independent Hamiltonian. So we know the solution of the Liouville von Neumann equation. But there's one super important fact here that makes being in the weak coupling limit so simplifying for calculations. So if you look at that equation here, here's the chemical shift precession. Here's the coupling. From a quantum mechanical point of view, what's going to be really simplifying here? They commute with each other. It doesn't matter what order we calculate the chemical shift effects or the J coupling effects, because if we have, let's just simplify to 2 spins, I and S, the I spin Z operator commutes with the I spin Z operator in the scalar coupling Hamiltonian, and it always commutes with the S operator. So in the weak coupling limit, chemical shift commutes with the J coupling. And remember, the Liouville von Neumann equation had a commutator in it. So the fact that these commute means we can calculate the chemical shift evolution independently of the J coupling evolution. And we can do the calculations in any order we want. If it's convenient for you to calculate the chemical shifts and then calculate what the J couplings are, that's fine. Or you can calculate the J couplings and then calculate the chemical shifts. In the strong coupling limit, that's not the case, because in the strong coupling limit, we'd have a term like IX, SX, and IZ doesn't commute with IX. And the calculations then become substantially more complicated. So for pretty much, I think, the whole part of the class that's solution NMR will pretty much assume we're in the weak coupling limit. And certainly if you're doing hand calculations to see how a pulse sequence works in the literature, you're almost always going to be assuming you're in the weak coupling limit if you're trying to do things by hand to see how the experiment works. The big exception to that will be experiments like Toxie experiments, where the whole point of the experiment is to make the shift difference between spins average to zero to get to the strong coupling limit. So we'll get to those in the down the road, but mostly if you want to analyze how a Toxie experiment works, you mostly run a computer simulation because of the complexities of the math at that point. So we can do the same sort of thing we did before. Here's our answer for the J coupling. Right? We have the unitary transformations acting on the density operator. We know what the Hamiltonian looks like. I can do expand and Taylor series and work out what all the matrices are. But it's way more simple once one does this to recognize that, again, we can create a fictitious operator space and treat the evolution as rotations in this space. So I still have a right-handed system. So here I'm wondering what happens to the I spin. So here's IZ, IX, IY. So that part is still right-handed. And now the Z-axis I decorate with an SZ. And that's the scalar coupling operator, right? The scalar coupling Hamiltonian had in it the operator 2IZSZ. And then I put another SZ on one of the transverse axes. And that kind of depends on what I'm trying to do, what operators I'm playing with. So here on the left, you can see I decorated IY with 2SZ. Whereas here I decorated I decorated the IX with the 2IZ. And depending on the problem, I have to pick one or the other. And this says, much like our other pictures, well, first, what's the angle? The angle is pi JT. That factor of 2 pi, I took the 2 to the normalization. So frequency times the time is an angle. So this says, under the J coupling, if I start with IX, which represents transverse magnetization, and evolve the J coupling, it's going to evolve into this operator 2IYSZ. And if I keep going, it's going to rotate back into the IX operator. Over here, if I started with IY, under the J coupling, I'm going to rotate towards minus 2IXSZ. And if I wanted to ask what happens to SX magnetization, I would just swap the labels. I would have two more figures that look like this. So all the matrices, multiplications, reduce to these 4 pictures. It's probably a good time to switch and draw some pictures on the board. I got to remember how to do this now. It's been a whole 5 days. Stop share. Share screen. Oops. And this will start to get to something that's critically important, And how do these symbols relate to what we see in an NMR spectrum? So let's suppose I apply a 90-degree pulse and I have IX magnetization. And so it's a Y pulse. And so I would write that I started with IZ. I applied a pi over 2 Y pulse, and I ended up with IX. At that particular moment, if I collected the spectrum, what would I see? You expect to see at the frequency of the I spin, you expect, anyone online see that? No, I'm going to do something about the lights. No, that's not lights.
In the phone.
Yeah.
And you could fix the tokens of it from the.
Okay. You expect to see it on what? Centered on the chemical shift of the I spin, and one doublet is shifted by plus IJ over 2 IJ, and the other doublet is shifted by minus IJ in angular units. So the difference between them is 2 pi j, and in frequency units it would just be j. Now remember that this I X operator really means I X identity, and the identity operator just says that the population of the alpha state and the population of the beta state are constant. We can't create spins. I've written the identity operator right in 1, 1. But I could say that that's the sum of this operator plus the sum of this operator. And what does this operator do to an arbitrary f? If I take this operator and say I have some arbitrary f. When I multiply them together, I just get C alpha 0. This operator picks out the alpha component of the cat, and therefore this operator is called I alpha. And this operator then is obviously called I beta. And if I take their difference and normalize, I get IZ. Because IZ is I alpha minus I beta. So these are different bases for thinking about the identity operator and Z magnetization. If I add them, I get the identity operator. If I subtract them, I get something like IC. So that this is IX S alpha plus IX S beta. And one of these is that doublest component. And the other one represents that doublet in the NMR spectrum. Now, which is which depends on the sign of the J coupling. So one has to be very careful to get the identification right. That's mostly important in the Trozy experiment, as you'll see later. Most of the time, we just call 1, 1, 1. So now imagine what happens to these two. Here I said what the spectrum looks like. Let's imagine we sit on resonance here. So we're just going to see one component looks like it rotates with a frequency pi j, and the other frequency looks like it rotates with a frequency minus pi j. As we're sitting on resonance, we don't care about the chemical shift. So right after the 90-degree pulse, if I draw looking down from the top, here's the x-axis, here's the y-axis. In now I need 2 colors, so if that's possible. Okay. So let's call this one the red. So after the pulse, I have some the magnetization, and I interpret this. This is the I-spin magnetization whose partner is in the alpha state. So let's take the simple case that this is a nitrogen 15. So my transverse magnetization is nitrogen 15. Here is my, say, amide. And I'm saying when I generate transverse magnetization of the nitrogen spin, what are the states of the hydrogen? Well, to an extremely good approximation, they're 50-50. 50% of the hydrogens are alpha, and 50% of the hydrogens are beta. And their difference is only about 10 to the minus fifth, so I don't see it here. So I have half of the magnetization belongs to the nitrogens whose partner is in the alpha state. And then half of the magnetization belongs to the partner in the beta state. But after the 90-degree pulse, I rotated them identically. I didn't apply a selective pulse to one doublet or the other, so I rotated them both onto the x-axis. And now what happens over time? Well, this one in my drawing has a positive frequency. So it rotates in this direction, like gravity. And this one, the green one, in my picture, has a negative frequency and it rotates in that direction. So the two vectors that started out on the x-axis start to rotate. And now, suppose I wait just the right amount of time that the green one ends up here, and the red one ends up over here. And I know what that time is because I need a 90-degree rotation. Pi j t should equal pi over 2. Pi's cancel, and t equals 1 over 2 j. So I know what that time is if I go to j complement. Now, how should I represent this thing? Well, this must be, the red one, must be IY. And what's the state of the S spin? I didn't do anything to the S spin, so it's still in its original state, which I call S alpha. And this one is minus I plus. minus IY S of A naught. So the total operator, here I call the total IX. The total operator here now is IY S alpha minus S of A naught. And to get the normalizations right, I multiply by 2, divide by 2, and call this 2 IY SZ. So to get the normalizations right, SZ magnetization is the difference in these two operators divided by 2. And you can go back and show that. So this evolution, the picture I drew that said IX operator gets transformed into 2IYSZ says that the two doublet components are becoming anti-parallel to each other. And we would, if at this moment we took an NMR spectrum, if now we turned on the receiver, what would we see? We would see now an NMR spectrum in which this component was upright and this component was negative. And we have to do a magnification because we have high Y. In the lingo, we say this is an in-phase doublet. The two doublet components both point up at the same phase. And this would be called an anti-phase doublet because the two multiplet components have opposite phase. So this would be also then called the in-phase operator for IX magnetization. And this is the antiphase operator for IY magnetization. The in-phase operator for IY would look like that. The antiphase operator for IX would then be 2IXSZ. So the remarkable thing about this language is we did these direct products, some purely mathematical operation to generate these matrices. We gave them symbols, but the symbols relate one-to-one to what's in the NMR spectrum. It's really astonishing. And we can easily understand, as in this picture, what the evolution looks like and how this connects back to these different symbols. It's really a profound conceptualization of the problem. And before this was thought up, when people were just working with matrices, it's astonishing testimony to how smart the pioneers of NMR were, because they actually learned things by multiplying all these matrices together and trying to make sense of things. Well, unfortunately, for the people online, you're having a hard time seeing this. I'll take a look at the video and see if it's any clearer in the video. And if it isn't, I'll make a picture and add it to the Dropbox. And we'll try to figure out somehow how to get better images. Today seems particularly bad. And all I can do is apologize. Share screen. So then once again, we end up with these simple trigonometric relationships. We just have to write down our picture of axes This has come up again, no? How did we get rid of it last time? Um, See if that helps. So like I said, the next few slides do a lot of matrix calculations to show you that this is right. And I'll just go through them and make maybe a few points as we go along. But this is really the important part, that we know how to rotate for chemical shift in pulses. That's the same as the block equations. And now we know how to do rotations under the scalar coupling. So again, here's just generating the matrices and multiplying them together. And then at the end, here is the answer for the one pulse experiment. And remember to find this is the density operator. To find the NMR spectrum, we have to take the product with the detection operator and then take the trace. So, now I've added in the J coupling. There's the detection operator. There's the result. And now when we take the trace, we find 4 lines. There's a line at the I spin shifted by plus pi j, I spin shifted by minus pi j, S spin shifted by plus pi j, S spin shifted by minus pi j, just like we expect. The omega 1s here, omega I and omega S, back in the beginning here of this calculation, I chose the starting density operator to be omega I times IZ plus omega S times SC. As I said, sometimes I'll drop the omegas and just have IZ and SC. The omegas came because the amount of magnetization, the equilibrium polarization, was H bar over either 2 or 4 KT. And I said, normally I don't write all the constants because I can put them back. But the omega I and omega S could be important. If we're doing nitrogen 15 and proton, omega I is 10 times larger than for nitrogen. So I have 10 times more proton polarization than I do nitrogen polarization. So if I'm doing a calculation, I may need to keep the omega I and the omega S so that I get the intensities of the signals right. Because the intensity of the signals are going to be proportional to how much magnetization I started with at equilibrium. If I don't care about that, if I'm talking about a proton-proton experiment, there's no point in writing omega I and omega I on with every operator because the proton polarizations are all the same. Except say a methyl group where I may need to keep track of a factor of 3 for the 3 methyl hydrogens. But here, trying to be more general, I want to keep track of the fact that I might be hydrogen and S might be carbon or nitrogen, and I want to keep intensities. I still don't need to keep the H bars and the KTs, right? Because those are constants for all the nuclei. I can add them in if I need to later, but there's never any point in writing them all the time because they don't vary from one spin to another. So this just went through and did all the matrix algebra to discover that we come to the result we expect. And you can go through the matrix algebra if you want. Now, it could be that our pulse was selective. What we just did was a non-selective pulse, so that in that case, maybe it is both hydrogens. So the Z magnetization for the I spin and S magnetization, Z magnetization for the S spin were both rotated into the transverse plane. But it could be, if we're doing hydrogen experiment and N15, we could tune the pulse to either be resonant with the nitrogen 15 or with the hydrogen, so that if we're resonant with the hydrogen, we'll rotate the hydrogen magnetization, but the S-spin magnetization stays on the Z-axis. And those are separated by hundreds of megahertz. We can't really generate a pulse that would rotate them both at the same time. So in that case, our operator has to be then the direct product of, say, an X rotation for the I spin and the identity operator for the S spin. Back when it was a non-selective pulse, the operator was an X rotation for the I spin, direct product with an X rotation for the S spin, as you would expect. So they have different matrices, and after the pulse, we rotate the I spin magnetization into the transverse plane, but the S spin magnetization stays on the Z axis. The S spin magnetization doesn't evolve. It's always S spin magnetization, and it's going to have a zero trace with the detection operator because it's not processing. And we just get a spectrum that only shows the I spin doublet, which is exactly what you expect. Say if you applied a 90-degree pulse on hydrogen, you'd be astonished to find a nitrogen 15 spectrum suddenly appear. So now I want to leave. Yep.
About that. Just about
Uh-huh.
that is on that.
Uh-huh.
If I look at the density matrix is 2 IYSC
Mm-hmm.
point in time.
Yes.
If I take the trace of that with the detection operator, which is I plus.
It's coming. We'll either get to it today or tomorrow. Good question. Hold it. So of course now we want to forget about the matrices for the most part and work on the symbols. So here is something I told you the other day. Here's what we mean by two operators being orthogonal to each other. We multiply one operator by one operator, we form the adjoint. Multiply it by the second operator, which means direct product, and then take the trace. Actually, I don't mean direct product here. I mean multiply the two together. Scratch the direct product business. And so, for example, if we're talking about 2 spin operators, each of these would be 4x4 matrices, and we would multiply them together. And then we take the trace, and that result will be 0 unless the 2 operators are the same. And if they're normalized, this bit in brackets would be 1. If they're not normalized, it'll be some other number, and we can always renormalize. Now, I'll sometimes write this as trace of the adjoint times another operator. And sometimes I'll write it like this, where this bar in the middle means what's on the left has to have the adjoint taken. Just like in the bracket notation for wave functions, the one on the left, the fact that the angle bracket goes the other direction means take the complex conjugate. Here, for operators, the angle bracket going the other way means take the adjoint. So this means multiply 2 operators together. This means take the adjoint of this one and then multiply them together. So you have to be a little careful about the notation. So now you know from geometry class that you can resolve a vector into its components and represent any vector by the sum of the vector components, usually unit vectors along I, X, or X, Y, and Z axes. We saw that we can resolve an arbitrary ket into a linear combination of basis kets. And now we can resolve an arbitrary operator into a set of basis operators. And that's shown here. So we have the density operator, and I can write it as a linear combination of some basis operators with some number, possibly complex, that represent how much of each operator is present. If you take the simplest case, and then we have a recipe for how to find these coefficients. We multiply on the left by the adjoint of some operator. And then we take the trace. And the trace will vanish unless j is equal to k. And then we have divide both sides, and we have the coefficients. So we have a recipe for finding the coefficients. It's basically the same recipe for finding the coefficients when we expanded the wave function, except we mean different things by forming the orthonormal trace in this case, sum in another case, integral in other cases. So here's an example. If I have one spin, I have a 2x2 matrix. It has 4 elements. So I could write any arbitrary 2x2 matrix as a linear combination of these 4 matrices. A matrix that has the 1 in the 1, 1 position, a 1 in the 2, 2 position, a 1 in the 1, 2 position, and a 1 in the 2, 1 position. And I happen to be able to give these symbols. We already talked about this being the operator I alpha because it projects out of an arbitrary ket the part proportional to the alpha spin state. I beta is the operator that projects out the part of an arbitrary ket that's proportional to the beta spin state. And if you think about this, what this one does, this one turns I beta into I alpha. And in quantum mechanics, that's called the raising operator, I plus. It takes beta to alpha. And then this one, if you work it out, it takes alpha to beta. And it's called the lowering operator and given a minus sign. So I can write any arbitrary matrix as a linear combination of these 4 matrices, but I don't like the symbols, I mean the matrices. So I replace the matrices with their symbols, and I could say any arbitrary density operator for a single spin is a linear combination of these four operators, the I alpha operator, the I plus operator, the I minus operator, and the I beta operator. And if I don't like that basis, I can change the basis because, for example, the sum of I alpha and I beta is the identity operator. The difference divided by 2 is SZ. So I can always replace I alpha and I beta by the identity operator and SZ operator in my expansion. IX is I plus plus I minus divided by 2, and IY is I plus minus I minus divided by 2I. So I can always replace the raising and lowering operators by IX or IY. So one set of bases are called the Cartesian operator basis, and the I plus, I minus, I alpha, I beta are sometimes called maybe the shift basis. I don't remember, but we can go back and forth. So the same density operator could be represented here as this linear combination of I alpha, I plus, I minus, I beta, or this linear combination of IX, IY, IZ, and the identity operator. And you can see the coefficients just get reshuffled, of course, reflecting this adding and subtracting and everything else. So any operator can be represented as a linear combination of basis functions. How many basis functions are there for a single spin? Obviously, 4. And if we have 2 spins, we have a 4x4 matrix. So there's 16 basis functions. Once we know how they evolve into each other, we're done, because we only have to work out the rules. Here we worked out the rule, for example, how Ix evolves under the scalar coupling into 2IYSZ. The only thing that ever changes in the problem now is how big J is and what the time is. We know the answer, we just have to plug in the numbers. So once we work out the transformation rules for these 16 basis operators, how they interconvert under our Hamiltonians, that part's done forever. The rest is just numerical. How big are the chemical shifts? How big are the J couplings? What are the times? The hard work is done once, and then it's done forever and ever. And that's, just a fantastic part of this. Of course, if you go to 3 spins, you have 64 basis operators, and you're starting to get a little tired of working out all the rules. So again, eventually you just turn the problem over to a computer. And it turns out that under the weak scalar coupling Hamiltonian, many of these operators don't interconvert with each other. So if we have 16 operators and they can all interact in a pairwise fashion, then we have 16 squared, which is 256 possible interactions, but most of them turn out to be 0 because of the weak coupling Hamiltonian. So the problem is simpler than it appears at first glance. So then, just I think to finish up for today, what does this mean for the Liouville von Neumann equation? So here, coming back, is the Liouville von Neumann equation. And now what I want to do is substitute in for the density operator, its expansion in the basis. So here I've substituted in for sigma of t, the sum of the b sub k's, the coefficients times the operators. And I've done the same thing over here, but summation commutes with commutator, so I can pull the summation out, and the numbers always commute with the operator, so I can pull out the numbers. So on this side, I have the time derivative, but the only thing where the time derivative comes in is the b's. The operators don't have time in them. And over here, I have these commutators. And I play my same game. I pre-multiply on the left by another operator, or by the adjoint of another operator, and then take the trace. I pre-multiply here by the adjoint of some operator and take the trace. And I can apply orthogonality here. So, and if I assume, and then, so that collapses the sum to only the case where J is equal to K. And I still have the summation over here. And I take this trace here, the trace of the adjoint of operator J with the commutator. That's a number at the end of the day. It's a number that has two indices, J and K. So I've called it omega JK. It's a number. And its definition is this trace operation divided by this trace operation in case these operators weren't normalized. And this is a generalized frequency. This is the frequency at which one operator evolves into another operator under this Hamiltonian. If H commutes with B sub K, the commutator is 0, and these two operators don't interact with each other, simplifying my life. If this term that survives the Hamiltonian is a chemical shift, looks like a chemical shift, then this is going to be the chemical shift of the jth spin, because it'll turn out that there's a delta function here, and I just get back the diagonal part of the matrix of omegas. And it could be I get something that looks like the J coupling in here. So all the possible terms relating the 16 matrices will come out of this calculation. I'll have a 16 by 16 matrix, and they'll have in it things that depend on the chemical shifts, the J couplings, et cetera, but it also may have a bunch of zeros, which makes my life simple. So I don't know, this next one just does it a different way. What it means then is I end up with an expression for the coefficients, these little b's, and it's quite common, and I'll adopt that notation, that these little b's get written as the time-dependent average of the operator. This really means take the operator, multiply it by the density operator, right, and do the summation and do the trace. So if you look back to last week's lecture, we said the expectation value of some operator was the operator times the density operator and then take the trace. So I'm saying here that these B's are the expectation value of the operator. Yep.
Stylized L is.
Oh, so here, sometimes you'll see in the notes, I call the commutator script L, which is called the Liouvillean, and it's irrelevant here. It'll come up, be more important when we talk about relaxation. But for some reason, I put it in. So I end up with then a set of coupled differential equations for the expansion coefficients, how much of each operator I have. And here's a matrix of frequencies that represent the evolution under the spin system. And this looks exactly like the block equations, except it's a bigger matrix. If we just had one spin, this column would be IX, IY, IZ, and then possibly the identity operator that we don't care about. And in here, we would just have the frequencies. Now, this could be a vector of 16 operators, And this matrix is going to have in it scalar couplings and chemical shifts. But structurally, it's exactly the same as the Bloch equation. It's a first order differential equation for a bunch of numbers that represent the expectation values of these operators. But as you saw on the board, the operators represent things in the NMR spectrum. So the expectation values of these operators are the intensities of the different lines you see in the NMR spectrum. Or Z magnetization, which we don't see in the spectrum, but of course we have Z magnetization. So we've managed to start with the Schrodinger equation, convert to the density matrix, which has all these matrices, apply a symbolic representation, and turn that back into an algebraic equation. This is just algebra. And you can solve this trivially with Python or any other computer program. But the key thing, again, is that these operators reflect observable things in the NMR spectrum, the multiplets, the amount of Z magnetization. And that's really what makes this approach so profound, is the direct connection between the symbols and the NMR observables. Okay, that's a good place. We covered a lot of ground. You can review, the PowerPoint will get uploaded. If the screen is illegible, I'll make a figure and put it in the Dropbox of what I wrote on the board. And tomorrow, one of the things we have to do is address the question about what does this mean for the detection operator? And also I want to make explicit for the two spin case, what exactly in the NMR spectrum do each of these operators connect to? I kind of indicated a little bit, but I wanted to make it, right, very formally right. And then, we mostly have the tools we need to now start looking at how pulse sequences work up until when you want to ask about relaxation, right? We don't have relaxation here. So eventually we have to ask, how does relaxation fit into this? But that'll be in another week or so. Any questions? One question on hold. Okay, and again, if you came late online, we have a special seminar up at Columbia, so I have to race uptown, and we'll have a problem session tomorrow for about 45 minutes after class for anyone who's available, and I'll post an answer key tonight for problem set 1. See everybody tomorrow.